All right. How you guys doing? I hear there's donuts, donut battles outside or something. Is it like a recruiter or something, or? Goodness. Some sort of somebody with donuts. That's the important part, right? Okay. All right. So last time we left off here, talking about reaction rates, talking about, okay, well, how can we find the rate constant if we've got some data? So I'll try to get a good example of that for you the next lecture or two. From here, I wanted to go into a short chemistry review. We touched on it a little bit already, but I want to flesh that out a little bit further and then kind of give you the sort of the big picture introduction to why we care about drinking water treatment. I mean, there's obvious reasons, but kind of from a regulatory standpoint and from a conceptual standpoint, what are the factors we really are concerned with dealing with. Okay, so moving from there. So chemistry. We did mention this, so going to just hit the high points here for this slide. When you take a look at the periodic table, we've got the different elements. We've got the atomic number up top. That's just like a list, 1, 2, 3, 4, 5. That relates to how many protons, but you don't really need to know anything about that. That's just the number. Here's the important number for any conversions from mass to mole units. So the number to mass, right? This particular car weighs about 16 grams per mole. I say car, molecule, atom, whatever, right? It's like how many, what does a dozen eggs weigh compared to what do a dozen Ford F-150s weigh, right? That's what we're dealing with, the difference in the mass to number. Okay, so when we are putting it together in some sort of a molecule, we're just going to add those based on what's here, right? So we've got oxygen as an example. Just a single oxygen atom is 16 grams per mole. If we have an oxygen molecule, so we call the stuff we breathe molecular oxygen. Molecular meaning it's not just an atom, it's a molecule. That's O2 gas, okay? Something you should probably just know. So that's molecular oxygen. And typically when we're talking about some sort of oxidation reaction, maybe we're growing bacteria, we're aerating the system, this is what they're using. That's what we assume. So O2 then is 32 grams per mole. Should be hopefully obvious. Ozone is another molecule made up of just oxygen. That's O3. We'll talk about that a little bit here and there. So it would just be 3 times 16 is 48 grams per mole. You could be precise, but with this number of decimal places, it's going to come out to very, very close to 48. Okay, so then ions. What is the difference between an ion and an atom or molecule? Well, an ion is charged, right? It can be a molecule, it can be an atom. H plus is an ion, and that's also just a single atom. So the ones we'll deal with pretty often in water chemistry is H plus. Essentially, that's where we get acidity in some sense. So that's a hydrogen atom. Sodium, calcium, and you see we just write it as 2 plus if it has 2 charges. Chloride, bromide, iodide, Cl minus, Br minus, I minus. So we got those atomic forms, pretty common. We have several common molecular ions. So if you remember from way back, polyatomic ions and all that. Here are common ones, and I'm going to talk about them a little bit. I'm going to give you a homework just to kind of practice using these. I don't actually care if you know the theory on, okay, well, why does it have exactly that charge? I just want you to have a working knowledge, okay? I'm not I'm not testing your Gen Chem knowledge. I'm just applying it a little bit, right? So you'll, in the homework, there will just be a table for you to fill out some things just to remind yourself that, okay, this is called phosphate. That's a 3- charge. As you add hydrogen atoms to it, you're going to make it sequentially less charged, right? So if you have HPO4, that's 2- instead of 3-, H2PO4, and then you could do H3PO4 if you want, but that's not technically an ion because it's not charged, right? That's why I didn't list it here. So that also brings us to acid-base systems and chemical equilibria, which we will talk about a little bit today, because that process of adding or subtracting that hydrogen, it goes both ways. That's an example of a reversible reaction. It can hop on there like something sticking to Velcro or pop back off. No big deal. If you have a whole lot of the hydrogens, it'll tend to add more onto it, just based on kind of probability thermodynamic stuff. We could say the same thing about sulfate here, SO4 2-. We could have HSO4- and H2SO4, get the sulfuric acid. We could have carbonate. This is carbonate here. We call this bicarbonate, and then carbonic acid. So those are a couple of common terms. The reason these are particularly important and always found in our water systems is really this is just CO2 gas that has dissolved in water. So when the CO2 dissolves in water, it turns into, if we keep both hydrogens on it, then that becomes H2CO3, which is what we said, the carbonic acid. Technically, that shouldn't be on the list either, these guys, but whatever. So we have some form of carbonate in water all the time. I guarantee there's some small fraction of carbonic acid in my water, probably more so some of this bicarbonate, and probably a bit of carbonate as well. So when you carbonate a beverage, you're just forcing a whole lot of it in there, and then you're causing it to stay put with the chemistry and with a sealed bottle. And then it fizzes when you drink it or when it's exposed to the atmosphere, because some of the stuff is bubbling out. And it does things for the taste and texture. Even water has important ions associated. We talked about H+ already. The conjugate of that is OH-. So water is in reversible reactions all the time with H+ and OH-. Okay. So basically, I'm just wanting you to be at least familiar with these polyatomic ions. There are more, and these ones in particular, the nitrate here is NO3-, nitrite is NO2-, and then hypochlorite here we will also deal with. So there's several, and I just want you to be pretty comfortable if I were to ask you, okay, just as a check, if I were to tell you you have 2.5 moles of nitrate per, in the swimming pool, what's that in mass? You should be able to calculate that based on, if you had a periodic table and you then remembered, okay, this is nitrate. I will go look up NO3. We know the O3, we talked about that a minute ago. That's 48 plus whatever nitrogen is, which is 14. So that it'd be 62 grams per mole. You know how many moles, so you multiply that, you get the mass, and you go on. So we'll have some practice here in a moment. But basically, my point is I just want you not to be like scared away of an ion or something. I want you to be kind of familiar. So stoichiometry. Heard that name, that term? This is really just a numbers balance. This is where and why we need to deal with molar units, right? That analogy of, how many eggs does it take to bake a cake, to egg a car, whatever. Like, there's a number requirement, right? Maybe it's 2 eggs per cake, and therefore you basically want to make sure you get the right number per the right number of cakes you want out, or cupcakes you want to yield. So because we have to work on the number amount instead of the mass amount, we need stoichiometry. And that's like, if this is eggs, and sugar. Well, let's maybe use something else. Let's say sticks of butter. Will yield X number of cupcakes. Okay, something like that is a decent analogy because it's saying, okay, we need some numeric ratio. If we want to scale up to 200 cupcakes, we need to scale up accordingly and not do this on a mass basis because we'll get confused and we'll get things wrong if we do it all in mass. All right, so enough of that. Let's do this actual problem. Stoichiometry. If we're talking about methane combustion, so CH4, basically we're going to heat it till it burns, and it's going to react with oxygen in the atmosphere. That's our combustion reaction. So stoichiometry, really what we're talking about is just based on the number of atoms in each molecule, we have to balance. We have conservation of mass, conservation of matter. So it's a mass balance just in chemistry. So I'm going to go ahead and arbitrarily say 1 for our carbon molecule, whatever contains carbon over here. So I know that on the left side we have just, and I'm going to pay only attention to the carbon first. Just take one thing at a time. In a combustion reaction, following carbon first usually makes a lot of sense. So it doesn't matter too much. You could start with whatever, but I'm going to go ahead and start with the carbon. Only 1 on the left side. If I say there's 1 mole of this or 1 molecule of this is going to react. Then on the right side, I need to make sure there's exactly 1 in the total of whatever we put over here. So I can put a 1 here. That's going to multiply by just the 1. 1 times 1 is 1. So we are good. We have 1 on both sides. Okay, so that balances our carbon. And I'll do the oxygen next. So we have some unknown amount on the left. And we already know we have to have at least 2 on the right, and then probably some amount of water. So over here, let's try 2. Well, technically, if I followed hydrogen, it would be a little simpler. The reason is because I have only 1 molecule over here that has hydrogen and only 1 over here that has hydrogen. You just have to go back and forth if you start with oxygen like I started to do. We could continue with just oxygen and then make a guess, but maybe the better thing is to say, oh, well, this is a little simpler if I know exactly we have 4 hydrogens here. The only place hydrogens can be over here is in that molecule, so let's go ahead and do 2 H2O, so that way we have 4 hydrogens on both sides. Okay, so then we know, then we've locked in how many oxygens we actually need on the right. So we have 2 here, and then 2 times 1 is 2 here, so that's 4 total, gives us 2 here. Everybody tracking that? Okay. Like I said, if you were silly and did it like I started to and just did oxygen, it would be like, okay, well, we have 1. Let's, we see we have at least 1 here and probably more. Let's guess 2, and then it would have worked out fine, but we would have had to check the hydrogens last and adapt it if needed, right? So it's okay if you don't remember or don't intuit the exact right process for it. You can get there. It'll just be a slight bit of trial and error. Okay, so take a minute and try this out for yourself. Put these pieces together. Let's say the question is posed, what mass of CO2 is produced if 100 grams of butane is fully oxidized? So it's really putting the last 2 slides together and making you do it. Yeah. You can work together. I'll let you know clearly if you can't sometime. If I'm legit doing a quiz or something and all that. But the point is for you to learn. So.
That's all. Now we have to go to doing the mass conversion that we learned the other day. So that's yeah, but so it's going to be 2 moles. Basically, we need to go there and there. So we need to figure out how many moles of butane, and then we need to figure out what the equivalent weight is in CO2. We're the same exact route.
Yeah.
So next up is like, yeah. Oh, so you have to balance left and right side. But we just have to balance 58 and CO2. So that's 12 plus 16 times 2. So we'll figure out the LCM between the two. So oh, but it's multiplied. Oh, so that's our ratio. That means this one thing, right? So we find our ratio right here, which is 58 grams to 44 grams. Use them to multiply them by the ratio, and multiply that into the grams and mass. So on one side,
All right. Looks like you guys
That's the fast
pretty much nearly done or done with the effort. Okay, so I'll walk you through it. Feel free to keep working. First of all, we need to balance the equation. You know, if you've got a bit of OCD, maybe you don't like having a fraction in the top. So, well, we'll get there in a second. It's probably okay. So you have one butane. I just set that to 1. So that means we need 4 carbons on the right side. So that's 4 CO2. Then I look back at the hydrogens. We've got 10. So I need 10 on the other side. That means we need 5 waters. And that means we need a fraction over there for the oxygens, 13 over 2, because we had 8 oxygens plus the 5 is 13. And for every oxygen molecule over here, it was giving us 2, so it would have to be 13 over 2. I don't mind. You could just leave it that way. That's fine as far as I'm concerned. Or you could multiply everything by 2 and get rid of that. So it's 2 butanes per 8 CO2, also requiring 13 oxygens and producing 10 waters, right? Okay, so then the other thing I wrote down was, all right, well, what are my molecular weights? And I'll go ahead and do that. So for butane, it was 4 atoms of carbon, which is 12. To do it on the board, I'm just keeping it simple and not doing the decimals when reasonable. So that's going to be 48 plus 10 for the hydrogens, so 58 grams. And to be really particular, which actually might help a lot, is I could write grams of butane per moles of butane. Maybe I'll just abbreviate. And then for the molecular weight of CO2, could write, okay, the 12 for the carbon and 16 times 2 for the oxygens. That's 44 grams of CO2 per mole of CO2. Okay, tracking so far? All right, so then we need to apply the stoichiometric balance, which is kind of the whole point of doing the comparison. This is our recipe. It's telling us how many of what do we need to yield the other thing, right? So that's what gives us the numbers comparison. And the numbers comparison here is 2 to 8, or which simplifies to 1 to 4, right? So the way to write that would be 1 mole of butane per 4 moles CO2. Or if we're looking at it the other way around, we could say we will produce 4 moles CO2 for every 1 mole butane. Because we are writing out the full units there, specifying which kind of moles we're dealing with, that's why we can just flip it, and it actually makes sense. So depending on which way you need to compare it, it'll work out. So with that, then we can say, all right, now we know the factor with which we have to multiply whatever this mass converts to in terms of moles to understand how many moles of CO2 gas we'll have out, and then we'll convert that to mass. Okay, so I'm just going to move this aside for now, or just get rid of this part. So that's our conversion. So we say, well, how many grams of butane do we have? I'm going to say, or how many moles? I'm going to say 100 grams of butane, and we can take this and apply our molecular weight. And you always have to check, am I multiplying, am I dividing? Just make sure the units match, right? Because we want to go from grams of butane to moles. So then we'd have to divide by 58 grams so that the grams cancel. Grams butane per mole. Butane. That way the moles of butane will come to the top. And so 100 divided by 58. Does anybody have that number for me? 1.72. 1.72 moles. Butane. Okay, so then we can take that 1.72 moles butane, and here's why I'm repetitively writing it all out for you. I don't always do it, but especially if I'm at all confused or like needing to closely track what's going on, it really helps to write it all out. So 1.72 moles butane, and then we can multiply that by that factor here. I'll just go ahead and write it out again. By 4 moles CO2. And here's where you can really recognize why we're doing 4 over 1 as opposed to 1 over 4, is because the units need to cancel, right? And it has to be, it's not just moles that are canceling, it's moles of what, right? So just track that. So we have moles of butane canceling with moles of butane to give us 1.72 times 4. Anybody have that for me? 6.8 something? 6.8 moles of CO2. Okay, so then we're almost there. We've done the conversion, so we had to convert from mass into a number unit. That way we could compare on a numbers basis. And now we're ready to, now that's gone through that process, we can go convert back to a mass. So here we take 6.8 moles of CO2 and multiply that by our 44 grams per mole. And that should give us our answer. If somebody has that. 303? 303 grams CO2. Okay, so what might be interesting, and I don't know if this is, heard somebody saying, that doesn't look right or something. What we see here is we've tripled the mass of whatever carbon compound we're dealing with by this combustion. And actually, if you go back and look at the compounds themselves, this is a mostly carbon compound. The hydrogens don't weigh a whole lot. So it's 48 out of the 58 is all carbon. Whereas CO2, this is mostly oxygen, right? It's like 12 parts by weight, 12 parts carbon and 32 parts oxygen. So anytime we're combusting something like that, we're losing the hydrogens, which don't weigh a whole lot. And we're adding oxygens, which do weigh a lot. And so by weight, we get a lot. And we also noticed that we had 4 carbons per one of these, so that's pretty dense, and we just have 1 carbon over there. So in that way, it makes sense even if it's surprising. Okay, does that process make sense? Any issues, questions? Okay, so I wanted to give you this kind of practice and work through it very clearly with you, because we'll just have to do this kind of stuff a lot, right? If this is uncomfortable, make sure to pay close attention to that on the first homework. I'll give you some practice. What I'll probably do is make the first page of chemistry review stuff optional, in case you're just like bored and falling asleep because this is just so routine for you. That's going to be the case for some students. So had more space for that. I don't think we need that. All right, so equilibrium reactions then. So whereas combustion was irreversible, we're not going to create butane out of water and CO2, at least not easily. If you do know how, then I think everybody wants to know. It takes, usually we rely on plants and bacteria to do that kind of crazy chemistry with, solar powered photosynthesis and all of that. Takes a lot to go in reverse. So typically we don't think of that, let's say methane or butane plus oxygen yielding CO2 and water. Yeah, I know I'm not balancing it. I'm just writing out the chemicals here. That's what we call a forward reaction or an irreversible reaction. There's no going back. And that's just because it's so energetic. And the thermodynamics will never let this reaction go backwards. It's not ever going to spontaneously reform methane or butane or whatever. That's a very different case, though, for a lot of things that are just kind of happy to be one way or the other. If we consider the combustion reaction, the irreversible, combustion's a good example. You explode a grenade, let's say. The grenade is in fragments everywhere. There's no coming back. Earlier I mentioned with that hydrogen hopping on or hopping off, kind of like Velcro. Well, if you tear some Velcro, apart, well, you can just put it right back. Right? There's that's reversible, presumably, right? You can go back and forth. It's no problem. So in one case, it's so destructive and it just, everything flies apart. No chance in coming back to the way it was. In the other case, it's pretty happy, right? So water is a good example of this. So we have H2O in a back and forth reaction, already mentioned it once, with hydroxide, OH minus, and H plus. And in fact, most of the time it's in water form. A little bit of it will dissociate. This would be called a dissociation reaction. So it dissociates from H2O to be HO and H. Okay, you could also call that partial ionization here. We have another common example for us in the class that we will have to deal with is chlorine. If it wasn't obvious already, we use chlorine for disinfection. That's why we have to deal with this in class, right? So we have HOCl. This is called hypochlorous acid. Can dissociate into the acid, which is H plus. So that would be consider our acid sort of. And then our hypochlorite. Okay, you'll probably see those terms in several problems. The point here is that it dissociates and it can be in either form. And if you have this active chlorine, this is the stuff in your bottle of bleach, by the way. At home, if you look, it'll say sodium hypochlorite. So that's probably a form of it that is, they added NaOCl, and really that dissolves and dissociates into Na plus atoms and OCl minus atoms. We do that because we don't like to keep it as an acid because it'll volatilize easier without having a charge. So your solution of bleach at home is going to have some base in it to keep it in the OCl minus form. It's a bit less reactive. It's less volatile, meaning you're not going to have inhalation hazards of noxious chlorine gas. So we like to do it that way for our bleach at home. And the sodium is just there to satisfy the other charge, make it, put it in that form. So, okay, so this is the stuff you have at home. Just a little side comment there. And what's important here is the pH of our solution. The acidity of our solution is actually going to tell us which form is it more likely going to be in. I mentioned earlier, let's take the Velcro analogy again, right? So let's say we're playing like the little sticky pad ball, like with a tennis ball sort of thing. You throw it to each other and it sticks on the pad. Well, let's say we have just a randomly bouncing sticky balls in a room, and you're trying to see how many of these pads are stuck with this hydrogen, this ball. Well, if you just have a bunch of pads on the wall and a bunch of these balls throwing around, if you have a lot of them, most of them are going to be stuck too, right? Most of them will have that proton added to it. If you have very few, then most of them are going to be empty and like happy to take one, but there's just not enough around. Right, so it's a little bit supply and demand. We'll push this reaction one way or the other just based on the acidity in the environment. If we're talking about these little Velcro sticky balls as the acid floating around trying to stick to the molecule. Okay, essentially when we talk about these equilibrium reactions, we form an equilibrium because both reactions are happening. We're sticking it on and we're pulling them off. And that's just going to happen by random diffusion and stuff in the water, just entropy. And so we will reach an equilibrium once we've given it enough time for those two rates to equal each other. So even if there's a different amount, and I'll show you a little video that kind of demonstrates this pretty well. Even if there's like mostly the OCl minus and a little bit of HOCl, the amount that they're changing is the same. So the amount of times you're pulling off the tennis ball versus adding a tennis ball though that rate at which that's happening is the same, regardless, if we reach equilibrium, that's regardless of how many have the tennis ball stuck. Okay, so it doesn't really matter where the balance is, it's just that we arrived at a balance. And for our class, we're not going to deal with the time leading up to the balance. I mean, we've actually learned the mass balance stuff that could let us do that, but it's not really typically relevant to the problems we're doing. So it's a thing we could do, but we're not really going to bother. We're just going to assume pretty much we've already reached equilibrium, so that we need to know about the equilibrium reactions, but we don't need to go that far into it. If there's an H plus present in the reaction, then that means it's pH dependent. So a lot of the systems we're going to look at are pH dependent. So changing the acidity or the amount of base or acid in a solution can manipulate our equilibrium reactions that are dependent that way. Sometimes we have reactions like a dissolution reaction. It's an equilibrium reaction. If you, let's say, add sugar to water, if you add enough of it, you're going to be, you're no longer going to be able to dissolve it. You've probably done this in elementary school. Supersaturated a jar of hot water with sugar, and then as it cools, you put a little thing in it, and it'll start crystallizing sugar crystals on it. That's an equilibrium reaction. The solution has some amount of sugar that's dissolved and some amount that's not. There's actually constant dissolution and precipitation. So precipitation, dissolution reactions are also equilibrium. It can go either way. And that sugar example is a time where you force it to start precipitating, and until you have enough of it in there, it's all just going to go to be dissolved, but eventually you can make it reverse. Okay, so I want to show you this little illustration about equilibrium reactions. See if I can get the in-class audio set up properly. So it might take me a moment with the sound. Just going to test it first.
Reversible reactions. So what we see here, to start off, we have colored water, some green water here, that represents our reactants.
Let's try that.
Side of our process. And then of course we have our empty container over here that represents our product side of the process. So in any given reaction, when you start the process, everything's a reactant. So we all have water over here, and that's a product. When you have a reversible reaction, or a reaction has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So our very first scoop, I'm using 2 another teachers. If everyone here is scoop, on the very first scoop, all of it is going to be reactant turning into a product, and none of the other. However,
so in this moment, we're not at equilibrium yet. So he's showing that process that I said we're not really going to worry about is getting to it, but this helps explain why we can get to different equilibrium spots. So I'm going to let him keep going, but I just wanted to point that out real quick.
very next time I scoop, some of my product is actually going back into my reactant side. Now if I continue to scoop like this, and continue to do this, you'll notice how at first the reaction went really fast. And at first, a lot of water was switching sides, going to the product side. But then it kind of seems to slow down a little bit. And at some point, if I continue to scoop, the amount that scoop in each direction become the same. So if I put 250 milliliters here, I only have 200 on this one, so I'm not quite there yet. Okay. So now I have 250 milliliters here, I have 225, so I'm getting closer. So I'm almost at equilibrium. And here I have 225, 225. So if we look, again, this is not perfect measurements, but if we look at our values, they're almost identical. We're showing that the amount that's crossing from here to here is equal to the amount going this way. Now the amount in the beaker represents the rate. so the rate of transfer is the same. From here on out, I can do this for a day, 2 days, 10 days, 10 seconds. It doesn't matter. This is at equilibrium. Okay? So the amount I take here goes here, the amount I take here goes here, and that process never ends. So this reaction now is basically over. Doesn't keep reacting. It just means it's not going to change it. So we've reached equilibrium. And so if we go back to the graph on our slide, we would see that this is the first one, the top one, where the rate flatlines becomes equal. Okay. Now, does it mean that we have to have equal amounts? If you look at our tub, because I was using the same size beaker, the volume of the tub is also very similar. So you would almost get the indication that maybe the amount in each side has equal. So it has to be 50% this, 50% that. And that's not necessarily true. If we reset our setup here, and we begin again, but this time, instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as a reactant. I'm going to use the little guy for my product set. Okay? So when I'm ready to scoop, again, it's all reactant, no product. Again, I start scooping, I get some product back to reactant. Now you might think there's no way you can get equilibrium here, because the big scooper will always outdo a little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam. Again, we're looking for equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at 140 milliliters. So if you look, these two volumes, even though they're in different size containers, again, are showing almost identical volumes, which means if I pour 140 here, and I pour 140 here, there's no difference. Okay, so I am now at equilibrium. Okay, so switching again, I can do this all day long.
Okay, so that explains kind of the concept behind why we might be at equilibrium with different amounts, right? So we might have a lot of OCl minus and only a little bit of HOCl, but they're going back and forth the same speed because there's a certain amount of acidity in the environment. So if we have lots of OCl minus, that means there's not a whole lot of acid around to add an H to it. They can be at equilibrium even though we are forming HOCl and dissociating at the same time, but those amounts are a little different. I'm gonna let them go for a moment longer in case there's something else I thought was interesting, but might just stop it in a moment.
And from this point on, there will be no change in the volume of either tub, which means this reaction from reactant side to product side is at equilibrium. Okay, I can see right on the wood, nothing changes here. Again, we have 140 plus. This particular scoop happens to be actually less in terms of what we have. Okay, it's not perfect with using scooping water. But again, we see 150 to 140, same amount of volume, crossover, equilibrium. Okay. Now in this case, if we look, we had equilibrium. So the process is at equilibrium. But if we look, on the product side, we have much more water than we do on the reactant side. Okay. So in this case, because we end up with more product, we would call this product favored equilibrium. We have less reactant, so it is not reactant favored. Okay? If you flip it, and it has a scenario where at the end.
Okay. All right. Does that help a little bit? Kind of conceptualize these equilibrium reactions. Great. Okay. So then, what we need to do then is understand kind of how to do the mass balances for equilibrium reactions. So, like I said at the beginning of this course, the chemistry is really going to come down to units and mass balances. So we're going to break it down to that point, give you the formula. It's a formula you'll have on your exam sheets to know how to deal with this quantitatively without too much more concern about how to know where the rates are going and all that. So the simple way to look at this then is to have reactants and products, and they're in equilibrium because it goes both ways. We can describe A molecules A, B, C, and D. So A and B are reacting together to form C and D. We don't have to have all of those, but a typical system might have 2 of each. Probably more often than not, we'll have for our equilibrium reactions, we're just going to have one thing dissociating into 2 products. That's going to be the most typical. But it doesn't matter. We can leave it in this form and describe it in this form with this equation. We're going to have some equilibrium constant that defines what the balance is by default. That's just based on the chemistry, based on the dynamics of the system, outside of our scope of caring how they derived it, because we're pretending like we don't love chemistry in here. So this K here, even though we could probably derive it with thermodynamics and stuff, we're just going to be given that. It's going to be known, or maybe what we're looking for, perhaps. It's going to be a constant. And so with that constant, what we're going to be looking for is to set that equal to the products over the reactants. But if you notice here, I put these in brackets. So that means, especially because this is a chemical reaction, that means we are dealing with numeric units, not mass units. So we have to compare these equilibrium reactions based on molar units. So the brackets, that means in moles per liter. Okay, so anytime we're dealing with an equilibrium reaction, just keep in mind we know that we're going to have to be in molar units, so we might need to convert. All right, so then the way to describe that mathematically would be to say this equilibrium constant is equal to the concentration, the molar concentration, the brackets here, of C raised to the C power. So this is just like when we did the CO2 stuff, right? It was the lowercase a would be 1 if we had CH4 as the uppercase A, plus, 2 oxygen. In that case, it was a forward. I'm just going to write it out real quick. And we said we were creating 1 CO2 and 2 H2O. Now, this is not the right reaction type, but I wanted to just show you that where the A's and B's are going, right? So this is, if we were to write that out, that would be CH4 to the 1 power times, those are the reactants. I'll just write the products here. That would be CO2 raised to the 1 power times H2O to the 2 power if that was our equilibrium reaction, which it's not, right? It's then reactants down here. So does that make sense where the 1 and the 2 are going and all that? Issues? Okay. So that's just how we're describing it, is with a chemical reaction like that, the lowercase is that the number of molecules beforehand. So we'll say number, so the lowercase is the number, and the inside the brackets, that uppercase, that means the concentration of that thing. And so then D would be molar concentration of D. Okay, so with that, we can write our equilibrium reaction in that manner. Turns out a lot of these are very simple. Like water, for example, is H2O in equilibrium with H plus and OH minus. That's already balanced, and everything is an exponent of 1. So it's very simple, right? I say it's very simple, but there is one caveat we have to deal with. Explain that in just a second. But in this case, we could write that as our equilibrium constant for water is equal to H plus times OH minus divided by concentration of water. as a liquid. Okay, does that make sense? All right, so the caveat is, what's the concentration of water? And the answer is it's kind of unity. It's like as much as you're going to get, it's not really going to change so much if you change some of it into H plus and OH minus. It's so concentrated that anytime you're dealing with a system like this, it just ends up not mattering. So to be technical, I think at around room temperature, the molar concentration of pure water is about 54, 55 moles of water per liter. And we could do that calculation if we wanted to. We know that 1 liter is 1 kilogram approximately, if that's 5 degrees Celsius. And we could do the calculation, okay, well, water is 18 grams per mole. If it's 1 kilogram, that's 1,000 grams. We could do all that, figure out exactly the molar concentration of water. But it turns out that, especially at the concentrations that these exist, this KEQ, by the way, for water, I'll just say KW, is 10 to the minus 14. So when we are fractionating some of it away from water, we're actually dealing with very, very small amounts of the water loss. So it's like 10 to the minus 7th moles per liter of H plus. If we compare that to 55 moles per liter, it just doesn't do anything, right? So when we have a liquid or a solid, we just treat that as one. The concentration of a liquid or a solid, whether it's like a precipitation reaction and there's a solid sitting in there, some of it's dissolving and some molecules are precipitating back. If there's a liquid or a solid, we treat it as one. And that's always going to be on the denominator because that's always going to be our reactants. It's like our solid is dissolving or our water is dissociating. That is like the actual liquid, the solvent itself, right? So that's not true for, let's say, HOCl. That's not a liquid, that's just something dissolved in the liquid. Okay. If it was purely hypochlorous acid as a liquid, that would be scary. Okay. Does that make some sense? A little weird that it works that way, but it works that way. So keep that in mind. That's kind of the one caveat. Otherwise, it's pretty straightforward as long as you use molar units. Should be okay. Okay, so this was the graph that was shown in that little video. So ultimately, once we reach equilibrium, we've got those equal rates. That's usually at the moment where we start analyzing our system. We assume that we add our chlorine and give it a few minutes. Usually these equilibrium reactions happen pretty quick if it's perfectly mixed, which is what we assume. Then pretty quickly we reach the equilibrium, and then what we're concerned about is, okay, how much of this is HOCl versus OCl minus? Because one of these is actually a better disinfectant than the other. And so that actually turns out matters quite a bit. So we end up ultimately favoring HOCl. We'll cover this more later. And it's a better disinfectant by a good margin. So something like a factor of 5 to 10. So if we design our system assuming we have the right amount of chlorine, but the pH changes and we didn't realize, we could be in big trouble because it could shift everything from HOCl to OCl minus. So this is why this is relevant, why we're going to have to work some problems like that. Okay, another way to visualize these would be to make one of these plots here to show some fraction of the different species. So I talked about CO2 dissolving, CO2 gas plus water gives us carbonic acid, do H2CO3. And it makes sense if you look, this is just CO2 added to a water. We just inserted a C there and added an oxygen, or two oxygens. Okay, so that gives us carbonic acid, which is why rainwater is naturally a little bit acidic. We get some dissolution of the carbonic acid that then releases some H plus. So when we do this reaction, it'll be HCO3 minus plus H plus to get that stuff. Or it can go this way and say H2CO3 is formed by the reaction of HCO3 minus plus one proton, one H plus. Likewise, we can say that's going to be in equilibrium with CO3 2 minus plus H plus. Really, probably the best way to write this would be what's actually in equilibrium there is not the combination here, but it's rather just the HCO3 minus. So HCO3 minus is in equilibrium with the CO3 2 minus plus H plus. So we kind of have those two reactions. So that gives us a series of equilibrium reactions, and depending on where our pH is, we can know that we're going to have more or less of one substance or the other. So if we have a neutral pH, pH 7 is neutral, we can say that, oh, well, I'm pretty sure that most of our stuff is going to be this bicarbonate, the HCO3 minus. That's going to be something like 85%. And then that leaves us with, 15 to 20% somewhere. So maybe it's 82 and 78 or something, or excuse me, and 18. Something like that, some fraction of the total is in one form or the other. And down here at a kind of a neutral pH, we actually have very little of the carbonate, direct carbonate, because you see this line comes all the way down very close to zero by that point. Okay, so that can be a useful way to look at it. And if we define a spot where they are equal, all things, all else, regardless of the pH or whatever, if we're interested in when those two species are equal, we can define those spots right there. And that's actually how we define our equilibrium. So when we said our K is equal to the products over the reactants, then if we think about it, when we set these two equal to each other, if we multiply both sides by the reactants, then K is essentially the, or let's say we set these two equal, products are equal to the reactants, that is K equals essentially 1 at that spot. Okay. All right. Don't worry too much about that. I may have just confused the matter a little bit. So, but just note that. Well, actually, you know what? Here's the thing. Sorry. When we do that, if I said products and reactants are equal, what I meant to say was the H2CO3 and the HCO3 minus are equal, because if those two are equal, then the only thing left is the pH, and that tells us at what pH are those two equal, right? So let me write this up properly, and then it will make sense. So if we do that, then we say K for the equilibrium is equal to the H, let's say HCO3 minus times H plus over H2CO3 minus, or excuse me, H2CO3. If we set the carbonate species equal, so right where they cross, right there, then the only thing that can change is the H plus. So then at that spot, the KEQ equals our H plus concentration. That's what I meant to say. Okay, so we can define them in that manner. You'll notice this once we start working with some problems that, at this particular pH, they're equal. This is actually why we know neutral water is pH 7, is because at pH 7, it all equals up. And I think I've got that right here. So let's talk about pH in general. then I'll come back to that same point a moment ago. But what does P mean anyway, this whole pH thing? The H is coming from the H plus, the acid, right? That's where the H is coming from. We could do POH. In fact, I think might have an example of that. But the pH, it's just like an algebraic function, just built in to the terminology. So what we're talking about here is this equilibrium of water dissociating into H plus and OH minus. And I mentioned earlier that equilibrium is 10 to the minus 14th. This would be a good one to commit to memory. It's relevant to pH systems. So the equilibrium constant for water is 10 to the minus 14th. It's really easy if you think about it as like a pH scale, goes from 0 to 14. The whole range that is possible for H plus or OH minus to go to on the extremes is up to 10 to the minus 14. And that's how we're defining it here. So if we write it this way, what we'll notice is this guy goes to 1. So really, 10 to the minus 14th is equal to the product of OH minus times H plus. So that's a pretty simple relation. We can always know, if we know something about the pH, then we know the ratio of OH minus and H plus. It's just always going to be that way. Likewise, if we knew the concentration of one of these, we do know the, assuming you commit this to memory, then you do know the other component. And so if you know the H plus concentration, you should know the OH minus concentration. They're inverted in that manner. So at pH 7, this is considered neutral because that's exactly where, if we were to plot again that fraction, the fractional amount versus pH, if we have 7 right here, well, in acidic conditions, we mostly have H plus. And then for neutral conditions, we mostly have OH minus. Or excuse me, basic conditions. Okay, so that means right here, the two are equal. That happens at pH 7 because when we have OH minus times H plus, that equals 10 to the minus 14th. Well, the only value that they are the same and that is true is essentially to say, H plus is equal to H plus. So we're saying the same thing, right? It's just one of them squared if they're equal, right? If OH is equal to, we'll just write it out. If H plus is equal to OH minus. Okay, so if that's the case, then it's writing the same thing. So that's just H plus squared. We could do OH minus squared, doesn't matter, equals 10 to the minus 14th. And the solution to that is H plus equals 10 to the minus 7. Just taking the square like that. And that means that's also equal to OH minus because of what we said. We're looking at the case when they're equal. And it's going to be moles per liter because we're in brackets, right? So all that to say that pH 7 is right where they meet, and this gives us some indication of what the P means, which is you take 10 to the minus blah is the P of blah, right? Or so let's write that out properly. So at pH 7, we just talked about that. pH is saying the negative log of that concentration. So the negative log of H plus is pH. That's the definition. So P of X is negative log of X. Does that make sense? So the P is an operator. So given that, we can say negative log of H plus equals 7. So that negative log of it if you remember log rules, that's essentially saying that H plus is equal to 10 to the minus this. The minus is coming from here, and the log rule is saying that's 10 to the what is equal to that. 10 to the what is equal to that, right? That's our logarithm. So that's our way of dealing with or simplifying our discussion there, or our computations there. All right, does that make sense? The pH stuff. Okay, P is an operator. Just remember that's 10 to the negative log of x is P of x. All right, so we've got just a few more minutes. So I'm going to go kind of make a quick overview of drinking water treatment, why we care, and our approach. So this will kind of conclude our recap stuff in terms of chemistry, mass balance things. And so we'll start getting into the core of the course content now. So next week, I'll probably post your first homework, and we'll kind of start doing some more in-class activities and things like that. Okay, so the fundamental motivation for drinking water, at least historically, was because we don't want to drink poop, essentially. Everybody's kind of nodding in agreement, makes sense, right? So if we imagine we have some sort of river it's flowing, and we want to use that, withdraw some water, put that in our nice little cup here to drink. Well, it turns out that upstream, invariably, somebody is using that water, and there's excrement, right? And more than likely, there's also some little animals, right? And I'm such a great artist, so I'll treat you to my little stick figure drawings here. Inevitably, we've got some problems, right? Some contamination. So this is the fecal-oral route of transmission that we don't want, right? So we've got fecal matter of some sort. Any warm-blooded animal will do. Humans would be especially hazardous because we don't want our gut bacteria to get to the wrong spot, right? We want it to remain in the place in our gut where it's happy and it's doing work for us. We don't want it to get to the upper parts of our gut where it doesn't belong, right? That's kind of it. If our guts were different, maybe we wouldn't care at all, right? Then we just care about the toxins or whatever. But the case is we don't want to get sick, right? So we do have wastewater treatment is one barrier. So wastewater treatment is great. Happy to do it. We'll talk about it. We usually add disinfection there as well, so that we are reducing the amount of fecal matter in potential water sources, even if that's drinking or even recreation, right? But inevitably, little animal's going to add its own contribution to our drinking water sources, and so we need the secondary barrier. And so this would be our drinking water treatment. Okay, so that's the quick and dirty version of why we care, right? There is more to it than that, but really the fecal-oral route of transmission, as funny as it sounds, is quite important and is one of the bases with which we consider our systems to design and to ensure our safety. So, as you might expect, where we get our water is going to matter a lot. If you were camping out on the top of a pristine glacier and you get a little bit of glacier melt, that water has never even sniffed a living organism before because it's just been precipitated, and then it was clouds, and then it was so evaporated, then precipitated, and it forms this glacier. Maybe it's fine to just drink it straight up, but that's not the typical situation, right? Usually, water we're getting has had some contamination or some potential contamination. So depending on where we're getting our water is going to inform how we treat it. We could even do desalination if we decide it's worth the cost to do so. So if you hear people concerned about us running out of water, it's actually just an energy problem and an infrastructure problem. We're gonna have water. Conservation of mass says there's going to be water on the earth, right? And then we have technology, we could desalinate it. There are challenges. Desalination is a lot costlier than let's say treating from the Mississippi, or even better, the groundwater here is what we use. There's, transportation and energy demands for the treatment itself are the bigger challenges. So the quicker we get good, reliable, quality energy sources, I think like nuclear, would be the safer we are from water shortages. Transportation can be an issue, though, if you like in a desert. I think our southwestern states are struggling lately because we ship a whole bunch of water and they extract a whole bunch from the groundwater, and the groundwater supplies are depleting a bit. So anyway, where we're going to get our water, essentially we can think of three different ways. Some surface water from a stream or a reservoir, so that's two of the ways, and then some sort of groundwater. We're not going to talk too much about desalination, but you could add that as maybe a fourth, or consider that perhaps an alternate surface here. From there, we have the water treatment system, the water treatment plant. It's mostly what we're going to talk about in the next section and a half, basically. From there, it's going to be shipped out to industries and individual homes. The distribution system itself sort of counts as part of the treatment train in a way, because it has to protect the water. We design it so that we keep a residual amount of chlorine. So it really is, in a way, part of our treatment process. Then it's going to go through and be used by people or industries, sent to wastewater. Talk more about that when we get to wastewater. But essentially, we want to collect and treat that, obviously. While we wouldn't put our own intake for a water treatment plant below our wastewater discharge typically, it's important to think about, because somebody's going to live downstream of you typically, and there's probably somebody living upstream of you typically, right? So ideally we would treat in such a way that we're not going to endanger the next user. It doesn't mean we have to make it perfect necessarily. At least our policy here is, when you're treating it, that's when you have to make it, like to drink, the drinking water treatment plant, that's when you make it perfect. Again, because in the environment, there's going to be some stuff we don't want anyway. Okay, so what impact has this had? Well, disinfection with chlorine kind of began sort of the turn of the 19th century. And we can see a correlated impact on typhoid fever. So typhoid is one of those fecal-oral transmitted diseases, and it is a relatively deadly one, especially before more of the modern medicines. And even today, if you decide to go somewhere in a less developed country where it's kind of a known hazard, there's more fecal-oral transmissions, less control of food and water, safety. A lot of times they'll recommend you get a typhoid vaccination so that you don't endanger yourself or bring back typhoid to potentially endanger other people, because it's a pretty bad one. And this typhoid, I believe, is also becomes pneumonia pretty often. So it can be pretty dangerous. It was pretty dangerous, especially here. You can see, 24, 25 people per 100,000 would die every year, which is quite a bit for something where you just don't drink the poop and then you're good, right? So by 1950s, we pretty much dropped that to nearly zero. Okay, so last little bit here. Really, our regulations for drinking water stem from the Safe Drinking Water Act in 1974. Of course, we started chlorinating pretty commonly before then, but this is when we really federalized and instituted national policies and requirements for anyone producing public water. This does not apply to private wells. There's no jurisdiction. You can go and drink from the LSU lakes if you want to. That's up to you. You could do that with your private well. You could drink it if you want to, like whatever, right? So that's not the government's business what you're deciding to drink on your own private system. But if they're going to serve you water, then they're obligated to make sure it's safe according to these criteria, right? So the primary standards, and generally safe in terms of toxins and pathogens, is kind of the general thing of it. So primary standards are health related, which means they're enforceable. So these are the ones that are truly required. We can differentiate them into chemical, radionuclides, and microbial. So not just eating the poop, there's also chemical and radiation concerns potentially. Secondary standards are pretty much aesthetic. That means they're optional. My water could be brown and smelly and warm and even potentially turbid, like kind of, just look all sorts of nasty, but I could drink it. It's like drinking lukewarm coffee. It's brown, it's smelly, it's got stuff in it, and you drink it, maybe, or you don't, right? Maybe you heat it up. But the point is, that doesn't say for sure that it's unsafe, but most people aren't going to want to. So they're definitely recommended for those standards. Hardness is the last one. Hardness is like a quality of water based. It's kind of mineral content that actually affects how soap works to an extent, and affects how much mineralization is going to happen if you like leave a faucet dripping or something. It's as stuff evaporates, you get mineral deposits. So I think I'll touch on that next time, and just go ahead and stop there. Okay, so have a good weekend, and we'll see you on Tuesday.